So once again, very good afternoon to all of you. So today I'm going to present my research work that is on performance investigation on six-phase induction motor drive. That is under the guidance of Dr. Rakesh Moria. So these are the outline of my today's presentation, and these are the objectives that we framed in our research work. And so these are the author's contribution. We have designed and developed the two type of six-phase machine that is known as six-phase symmetrical and six-phase asymmetrical machine. We have performed a comparative study of three-phase and six-phase PWM technique. We have developed a 24 sector based SVPWM technique that can reduce the current distortion features. So this thing that we have, sir, if you observe this table very carefully, the first three techniques are actually reported in literature. Remaining all techniques are actually developed and designed by us. Some of the techniques are good that can reduce the stator current distortion. Some of the techniques having the feature that can easily implemented, and some of the techniques are available that can reduce the switching loss features. So there are the development of 24 sector based SVPWM technique that can reduce the current distortion, that can easily implemented, and some PWM techniques are developed that can reduce the switching loss feature. In addition, we have also developed a switching table based direct torque control technique for six phase asymmetrical machine. Now let us discuss about the literature survey. So in case of three-phase machine, when power ratings are going to be increased, these particular systems are exhibit the poor performance. And because of that, multi-phase induction motor has emerged as a promising contender. There are mainly two things because of that multi-phase induction motors are widely popular. That is known as a power segmentation and reliability. When you increase the number of phases, power for phases are going to be reduced, and because of that cost of semiconductors are going to be reduced. And second thing is that whenever faults are occur in any one of the phases or maybe possible two of the phases, then also machine can produce a rotating magnetic field, and because of that we can say that the machines are more reliable. These are the mainly two reasons in nowadays people were prefer to use multi-phase induction motor. There are the types of multi-phase induction motor. In the literature, 5-phase, 6-phase, 7-phase, 9-phase or more than 9-phase machines are available and they are reported. Based on spatial displacement, asymmetrical and symmetrical machines are widely utilized in case of multi-phase induction motor. In case of asymmetrical machine, we are having a spatial displacement that is pi by n degree, while in case of symmetrical machine, we are having a 2 pi divided by n phase displacement between the two consecutive stator phases. Now let us discuss about the application of multi-phase induction motor. So these are the few applications where you can find out the multi-phase induction motor. Most of the time, multi-phase induction motors are widely utilized for high power and high current application. This is the selection of six-phase machine. The selection of six-phase machine is due to it can be realized by the conventional equipment. So six-phase machine can be run by using three-phase dual inverter. And there is one other advantage of six-phase machine is that the six-phase machine can be reconfigured as a three-phase winding or three-phase machine. And because of that, it will open one additional research domain that is known as a comparative study of three-phase and six-phase machine. And because of that, we have selected six-phase machine for our analysis purpose. To understand and to develop the mathematical model of six-phase machine, first of all, symmetrical components are need to be understood first. Remember that in case of three-phase machine, we have total possible three configuration. That's what we conventionally known as positive sequence, negative sequence, and zero sequence. In case of six-phase machine, we are having total 6 possible configuration, or you can say that 6 possible symmetrical component. Out of this, only this first and second, that is known as positive and negative component, they can only produce the rotating magnetic field. Remember that remaining 4 configuration can only present in the stator and they cannot interact with the rotor. So if we observe the equivalent circuit carefully, this is the equivalent circuit for DQ component and this is the equivalent circuit for XY component. The rotor part is present only for DQ component while XY component is only present in the stator. Our ABC components are required to transform into DQ component, and that's why we are having a Clark and Park transformation. So you can observe here, this is the transformation matrix for asymmetrical and symmetrical cases. These are the modeling equations that we have utilized to develop the mathematical model. So these are the voltage equation, these are the flux equation, current equation, torque and speed equation. So these all equations are ultimately utilized to six-phase mathematical development of mathematical model. Remember that this particularly two block transformation matrix and six-phase induction motor mathematical model will remain as it is. Our all works are mainly focused on six-phase voltage generation. So maybe possible we will use a PWM technique, maybe possible sometime we will use a transformer to generate the six-phase voltage. So this is the mathematical modeling of six-phase asymmetrical motor. All the equations that we discussed as two slides back are actually utilized here to develop the mathematical model of six-phase machine. Now let us discuss about the symmetric diagram of six-phase induction motor drives. So what we require in case of six-phase asymmetrical machine, we require six-phase supply, and that's why our conventional three-phase supply is rectified and converted into DC. That DC supply are converted into six-phase by using two three-phase inverter. What we also require, we require to sense the current and we also require to sense the speed. And that's why we have a current sensor and speed encoder. So current input from the current sensor card and speed input that is given to our microcontroller. The speed that we require that we are inputting from this key interface. This controller will generate the gate pulses we require to isolate and amplify. So gate driver circuits are used to amplify an isolated circuit, and that pulses are given to our six-phase inverter. So this symmetric diagram are also you can explore by using hardware connection. So this is the photograph of experimental test bench. So we are having a three-phase supply. That three-phase supply is given to our first of all isolation transformer, and that transformer will generate again three-phase voltage that we have applied to our two inverters. These two inverter will actually share a common DC link voltage. Output of these six-phase voltages are connected to our six-phase asymmetrical motor. To sense the current, we are having two current sensor card. To sense the voltage, we are having optical encoders, and ultimately they all are connected and given to STM32F4 controller. Pulses generated by STM32F4 controllers are amplified by using this two driver card, and it is isolated and dead banders are also provided, and finally it is given to our inverter. Remember, we also want to measure the parameter. For parameter measurement, we require conventional star delta transformation to get the ultimately asymmetrical three-phase supply. And because of that, we have used delta star transformation. So this is the connection of delta star transformation. This will use to perform the standard test. That what we call it as a no load and block rotor test. Remember, in this particular case, we have also required to measure the zero sequence test. So these are the connection and these are the result. So these are the results of our test performed, that is no load, block rotor and XY and zero sequence test. And based on that this test result, we have measured our machine parameter. These parameters are utilized in our all mathematical model and as well as our hardware analysis. We also want to perform the three-phase and six-phase PWM technique comparison, and that's why these six-phase machines are reconfigured as three-phase machine, and we have also measured the parameter. So these are the parameter of three-phase machine when six-phase machines are reconnected as three-phase configuration. So first task that we are going to perform, that is comparative study of three-phase and six-phase PWM technique. There are many paper or literatures are available. They compare the efficiency, reliability and torque enhancement. While in this particular case, we are going to perform the comparative study by actually analyzing the stator current ripple in three-phase and six-phase case. So first of all, let us try to understand the six-phase SVPWM technique. In three-phase case, we are having total 2:3, that is 8 possible switching configuration. While in six-phase case, we are having 2:6, that is 64 possible configuration vector. So these are all 64 possible vector configuration that are mapped in DQ and XY plane. Remember that we have to control our reference vector in DQ and as well as XY plane. So we require to control 4 variable, and that's why we require each and every time 4 voltage vector selection in case of 6-phase SVPWM technique. So these are the existing 6-phase SVPWM technique that utilize this 4 voltage vector. Remember, average of this voltage vector will be equal to your reference vector, and these vectors are selected and dwell times are selected in such a way that their average value in the XY planes are going to be 0. The second PWM technique that we selected for comparative study, that is sinusoidal PWM technique. So we have analyzed sinusoidal PWM technique using space vector approach to find out what are the voltage vector utilized by sinusoidal PWM technique. So these are the conclusion over here that sinusoidal PWM technique during the first sector that will utilize these 5 voltage vectors, and after 2 interval, or you can say that 2 sector, they are utilizing this voltage vector uh, for measuring, or for you can say that reference to generate a reference voltage vector. The second PWM technique, that is double zero sequence injection based PWM technique, are also analyzed, and here also the conclusion is that they are utilizing this 5 voltage vector in first sector and they change its pattern after 2 sector, that is in sector number 3 they are utilizing these voltage vectors. So these are the 3 PWM technique that we have selected for comparative study of 6-phase and 3-phase PWM technique. In case of 3-phase PWM technique, we are selecting this 3 PWM technique. Our performance parameter are mainly stator current ripple. So to measure the stator current ripple, initially we want to calculate the harmonic flux trajectories. So these are the equation that we use to calculate the harmonic flux trajectories. So when we calculate the harmonic flux trajectories, these are the result of harmonic flux trajectory that we integrate. Then when we integrate, we will get the RMS value of harmonic flux, and finally we will get our harmonic distortion factor. This is the very important factor, harmonic distortion factor, that is actually a measure of stator current ripple. But as our particularly SVPWM techniques are operated in 2 plane, we require to calculate total HF by using this equation where zeta represent your leakage coupling coefficient. So these are the results that we obtain for all PWM technique, 6-phase and 3-phase PWM technique. And remember, this is zeta value, zeta equal to 1, 2, 6.2 and 10. These are the value of leakage coupling coefficient that we selected to measure our 6-phase and 3-phase PWM technique. The zeta value is very common values, that is in between 1 to 2 if your windings are single layer winding, and for double layer winding the zeta is ranging from 6.2 to 10, and that's why we have calculated our HDF for this different values. What we conclude over here is that this PWM technique number 6, that is 3-phase SVM technique, have a lowest HDF. So you can say that it will provide a lowest stator current distortion or lowest THD among the all PWM technique for all the values of zeta. We have also calculated the analytical and simulation result. How we calculate the analytical result? By utilizing this equation. We will put the different values of HDF, we will put the machine parameter, and we will calculate our stator current ripple for 6-phase and as well as 3-phase case. In simulation, we have generated gate pulses and we will use our mathematical model to calculate the simulation result. We can conclude over here is that this 3-phase SVM technique that will provide a lowest stator current distortion among the all 6 PWM technique at 4.8 kilowatts and even at 9.6 kilowatts also. In simulation, it is possible to lower the values of leakage coupling coefficient. So these are the parameters, that other parameter that we use to calculate the simulation and measure the simulation result again with lower value of leakage coupling coefficient. So these are the simulation result. We can observe here is that now 3-phase result and 6-phase result are slightly comparable, though 3-phase results are still having a good advantage as far as waveform quality is concerned. These are the simulation result that we obtain at different values of modulation index, or we can say that different values of speed. Still, 3-phase machine having an advantage that it can reduce the stator current distortion. These are the experimental result that we obtain at different speed, and among that we have represent only one result. What we can conclude over here is that 3-phase PWM technique is having an advantage in comparison with 6-phase PWM technique. These are the results that we obtain at different modulation index. What we can conclude that the three-phase PWM technique provide the quality waveform, and we will get the idea that now we have to work on six-phase PWM technique such a way that we can reduce the six-phase PWM technique current distortion. So what we have found out that the 24 sector based 6-phase SVPWM techniques are very popular and they are widely accepted because among the all PWM technique, 24 sector based SVPWM technique will provide a lowest stator current distortion, and that's why we have selected 24 sector based SVPWM technique. So these are the all PWM techniques that we are going to analyze in this particular research work. First three techniques are reported in literature. The remaining these three PWM techniques, six-phase SVM2, B1 and B2 are provide a good performance at low value of leakage coupling coefficient. Low value of leakage coupling coefficient means zeta equal to 1. So it means that if I am having a permanent magnet synchronous machine, this PWM technique will provide me a lowest stator current distortion. This PWM technique, this blue one, 6-phase SVM3, B1, B2, 5, B1, B2, that will provide a better Ph.d performance for any value of leakage coupling coefficient. This last 6 PWM technique, that will provide me a easy implementation feature. So this PWM technique can be implemented and it can be utilized very easily. So these are the PWM technique that can provide me a good harmonic performance. And we have also developed these three PWM technique. These PWM techniques are designed and developed in such a way that they can reduce the switching loss effectively. So we cannot analyze all PWM techniques in a single analysis purpose, and that's why we have break down this PWM technique. So first of all, we have selected the continuous SV PWM technique. The question is that how we can select the continuous, or how we have developed continuous PWM technique. We have utilized the carrier based PWM technique and we have removed one voltage vector. So when we remove the one voltage vector, we are having these are the possibilities. In that possibilities we have utilized. So these are the result of all continuous PWM technique. What we can observe here is that our newly developed PWM technique, that is 6-phase SVM3. 6-phase SVM3 is having a lowest HDF. Lowest HDF, it means that they can produce a lowest stator current distortion among the all continuous PWM technique, including our existing PWM technique, that is 6-phase SVM1. To analyze this further, we have used analytical and simulation result. So this is the equation that we have used to calculate the analytical and simulation results. What we can conclude over here is that our newly developed PWM technique, that is 6-phase SVM3 technique, that provide a lowest stator current distortion at all the values of modulation index, or you can say that at all the values of speed range. In simulation also, in analytical result also, we have ultimately confirmed that this 6-phase SVM3 technique that can provide a lowest stator current distortion among the all PWM technique. These are the implementation steps that we have used for development of our PWM technique. And these are the experimental results. So in experimental result also, this is confirmed that this technique, 6-phase SVM3 technique, that can produce a lowest stator current distortion among the all PWM technique. While this technique, 6-phase SVM PWM technique, that can produce a higher stator current distortion among the all PWM technique. So we have also analysis further, and we will take the different values of modulation index and we have plot the curve. So this curve also confirm that this newly developed PWM technique, 6-phase SVM3 technique, that can reduce the stator current distortion very effectively. Now let us discuss about the discontinuous SVPWM technique. First of all, let me introduce the discontinuous SVPWM technique. Means what? In discontinuous SVPWM technique, we have removed one zero voltage vector. So if we observe these two switching sequences, in this particular switching sequences, we have not utilized zero voltage vector, and here also we have not utilized 63 number of voltage vector, that is also zero voltage vector. So because of that, we are having a clamping of one phase or maybe possible clamping of two phase, and we can say that our switching are not continuous, and that's why this technique are known as a discontinuous PWM technique. So this is the existing PWM technique that can be utilized to derive the discontinuous PWM technique, and these are the another three PWM technique that we selected. They all are newly developed PWM technique for our analysis purpose. These are the simulation HDF result that we obtain. In this particular result, what we can conclude that for lower values of leakage coupling coefficient, this newly developed PWM technique, that is the technique number 4 and our technique number 6, that can provide, or technique number 5, that can provide the lowest stator current distortion. But at higher values of zeta, if we observe the higher values of zeta, our newly developed PWM technique can produce higher result, while the existing PWM technique, that is the 6-phase SVM1B2, that can result in lowest HDF. This analytical and simulation result also confirm the same thing, that the 6-phase SVM2B1, because of these higher values of zeta, our newly developed PWM technique produce higher stator current distortion, while existing PWM technique will produce a lower stator current distortion. In simulation, it is possible to lower the values of leakage coupling coefficient. So by changing the parameter, we can reduce the lower value of leakage coupling coefficient. So at this value, this newly developed PWM technique can produce a lower stator current distortion. These are the results that we obtain with zeta equal to 1. And our conclusion here is that this technique, 6-phase SVM2B2, that can produce a lower stator current distortion at higher modulation index, and 6-phase SVM2 that can produce, or that can actually result in lower stator current distortion for lower values of modulation index. These are the experimental results. In experimentation, it is not possible to change or alter the values of zeta, and that's why this newly developed PWM technique can produce a higher stator current distortion in comparison with existing PWM technique. So here we can conclude that this newly developed PWM technique can be utilized only for lower value of leakage coupling coefficient. It means that if my machine having a single phase layer winding or maybe possible permanent magnet synchronous machine, we can think about this PWM technique. Now let us discuss about the another discontinuous PWM technique. Remember that due to utilization of 56 and 7 vector, you require some kind of discontinuity in your carrier wave. So to avoid that, we have developed this newly developed PWM technique that can never utilize 56 and 7, and that's why they are having a easy implementation features. So these are the requirement, and now let me discuss about the analysis of switching loss. Previously, we have discussed the continuous PWM technique where switching loss remains same. But in case of discontinuous PWM technique, your switching loss are going to be varied. So these are the equation that we have utilized to calculate the switching loss. The conclusion is that existing PWM technique 6-phase SVM1B2 that will result in a lowest stator current distortion. These are the harmonic result at different values of zeta. The conclusion over here is that the newly developed PWM technique, that is 6-phase SVM3B2, that can provide a good harmonic performance, or you can say that lowest stator current distortion. We have also calculated analytical and simulation result by utilizing this equation. This equation also confirms that this newly developed PWM technique 6-phase SVM3B2 that will result in the lowest stator current distortion in analytical and as well as simulation result. If we observe the waveform very carefully, this is also confirmed that 6-phase SVM3B2 that can provide or that can produce a lowest stator current distortion among the all PWM technique. One important thing is that this 6-phase SVM6 and 6-phase SVM6B2 actually they are providing a higher stator current distortion, but they can be produced or they can be generated very easily. So if you observe this waveform, again this will confirm that 6-phase SVM3B2 will provide a lowest stator current distortion among the all continuous among the all continuous as well as discontinuous PWM technique. Now let us discuss about how to reduce the switching loss. We have concluded that all the PWM techniques provide a better stator current distortion, but they can still produce a higher switching loss. So to avoid the switching loss, we have developed the 3 new PWM technique, that is 6-phase SVM1S1, 6-phase SVM3S1 and 6-phase SVM3S. How we have developed this PWM technique? That to understand that thing, we have to understand the modulating waveform. The existing and newly PWM technique both are clamping the phases at different interval, but they are not continuously clamped. So that's why we have designed this 3 PWM technique that can be actually continuously clamping the phase after 90 degree. After 90 degree, the reason is that our most of the current will attain the peak, that is after 90 degree, and that's why we are designed and developed in such a way that they are clamping the phase whenever the phase currents having a maximum peak. So these are the normalized switching laws for different PWM technique, and these are the result of normalized switching laws. Here we can observe that our efforts are going to be worse. We have developed the new PWM technique, 6-phase SVM1 3S. They are recorded with the lowest switching loss among the all PWM technique. These are the analytical or simulation performance evaluation of different values of HDF. We can conclude here is that 6-phase SVM3B2. This is the second technique. They can be reduced stator current distortion very effectively in all the other PWM technique. In case of 6-phase 6-phase SVM13S, they are produced slightly higher stator current distortion. Analytical and simulation result also confirm that this PWM technique 6-phase SVM3B2 that can produce or that can reduce our harmonic distortion effectively. But if we talk about the switching loss performance, this PWM technique 6-phase SVM13S will produce a lowest switching loss. Now let us discuss about the experimental result. Experimental result confirm that this 6-phase SVM3B2 can produce a lowest stator current distortion among the all PWM technique. This experimental result when extended with other frequency that also confirmed that this PWM technique number 6-phase SVM3B2 can produce the lowest stator current distortion, while 6-phase SVM13S will produce slightly higher stator current distortion. But the one important point that is to be noted here is that though they can produce slightly higher distortion, but this PWM technique number 5 reduce switching loss very effectively. The percentage reduction of switching loss is very high in comparison with the increment of stator current distortion. After that, we have shifted our analysis from normal PWM technique to direct torque control or advanced control technique. In advanced control technique, we have selected the direct torque control technique, that is switching table based control technique for implementation of DTC in 6-phase induction motor drive. So these are the equations that we have used in case of implementation, and this is the schematic diagram. Power diagram will remain same, only software part is modified. So here we are using the current and speed and voltage input. We are actually measure the flux, torque and angle estimation. And this flux, torque and angle estimations are used to calculate by utilizing the 3-level or 2-level hysteresis controller and lookup table technique to generate the pulses, and that pulses are fed to our 6-leg inverters. The first technique that we use, that is the conventional switching table based DTC. In conventional switching table based DTC, in every sample, we are actually utilizing only one voltage vector. And because of that, we cannot control the XY current harmony. We have also selected one more PWM technique that is known as a modified switching table based technique. In modified switching table test technique, we have used this factor, that is 73% and 26% time. We are applying two voltage vectors. It means that 27 and 10, these two voltage vector will be applied for 73 duration and 26 duration. The 73 and 26 duration will be selected. Based on that, their average value on the XY plane are going to be 0. So this is the simulation result of conventional DTC. As we in conventional DTC, we are utilizing only one voltage vector, and because of that, it is suffer from XY harmonic, or we can say that 5th and 7th harmonic. This is the torque ripple. This is the flux. We can observe here is that stator flux on the XY plane is having higher magnitude. This is the simulation result of modified switching table based direct control technique. Here we can observe here is that because of utilization of two voltage vector, this can be, or you can say that XY harmonics are completely removed, and that things are also going to be observed in our stator flux trajectories, where XY plane harmonics are having a very lesser magnitude. Simulation results are also obtained at different values of speed and at different values of load to measure the stator current Ph.d. What we can conclude here is that modified DTC will reduce your stator current DTC very effectively in comparison with conventional DTC. We have also observed the simulation result at different transient condition, where we have changed the command of speed, and we have observed here is that our torque or reference and and measured torques are effectively tracked. These are the another dynamic result that we obtain at different loading condition. We can observe here is also that our motors are captured or ultimately attain the steady state speed even at this type of transient loading condition. These are the experimental results that we measured. So in experimental result, we can conclude here is that because of the conventional DTC that is utilize only one voltage vector, we have observed the fifth and seventh harmonic and XY current harmonics having also very higher magnitude, while it will ultimately track our reference flux and reference speed effectively. While in case of modified DTC technique, we have utilized the two voltage vector, and that's why XY harmonics are going to be reduced, and the peak or magnitude of XY harmonics are also very less. And here it is also tracked the estimated stator flux and estimated speed very accurately. These are the dynamic response that we have observed in case of modified and as well as conventional STDTC. So summary is here is that the conventional STDTC suffers large stator current harmonics, and because of that it will lead to higher stator loss and poor efficiency. While modified DTC technique that uses large and medium voltage vector, and it will minimize the stator current harmonic effectively. Conclusion. So let us start with the first our research objective, that is comparative study of three-phase and six-phase PWM technique. What we have observed here is that three-phase PWM technique that can reduce a harmonic effectively in comparison with six-phase PWM technique. In case of 24 sector based PWM technique, first of all, we have observed that this PWM technique, six-phase SVM3B2, that will provide a lower stator current distortion among the all PWM technique for zeta value that is equal to 2. For lower values of zeta, six-phase SVM3B2 can provide a lower distortion current, but only for higher modulation index. For lower modulation index, we have to shift from discontinuous PWM technique to continuous PWM technique. The performance of six-phase SVM2 technique and its discontinuous sequences is found superior only in the case of lower value of leakage coupling coefficient. In this particular research work, we have developed the 6 additional switching sequences. 2 of them are selected for implementation. This PWM technique produces higher current distortion. However, there is no modification in the carrier waves are required, and that's why these techniques are easily implemented on controller. We have also developed the 3 additional switching sequences. The aim here is to reduce the switching loss of inverter, and these techniques are effectively reduce the switching loss that we have observed just now. In case of direct torque control technique, we have selected the 2 techniques. What we have observed here is that the conventional PWM technique actually results in very high stator current harmonics, while modified switching table technique is actually reduce the stator current harmonic very effectively, because in each and every case they are utilizing the 2 voltage vectors, and they always reduce the harmonic from XY plane. These are the future scope that can be implemented in future. So these are the list of publication from this research work. These are the references. Thank you, sir.
Well, Suel, for very nice and crisp presentation you have given for your Ph.D. thesis, and very nice presentation, I must say. And now I would request our external examiner, Mr. Professor Ashish Kumar Sen, to kindly interact with Mr. Suhail and have your question and answer, please.
Yes, sir. Now audible.
Now it is clear. So you kindly go ahead, please.
Please. So, thank you, sir. Thank you for giving me this opportunity. So, I have gone through all these comments of the examiner in form of compliance report of examiners provided by the supervisor to me. So, I'm very happy to see that all the queries have been answered very appropriately in that. So, on that basis, I will say that there shall be no queries from my side in this process for today. But for the sake of I shall say for the exam, this examination process. So first of all, I will say thanks to the institution for giving me an opportunity to be the examiner of such a nice thesis. I appreciate the quality of work done in this, and the title has selected is excellent because this is one of the rare works which are being performed nowadays for this machine design process. So, and I also appreciate the candidate, Mr. Sheikh Mohammad Sohail, that he has done this work and he has done very much justice with the title and theme of the his thesis. And I really congratulate him for doing such a successful work, such a nice work, supported by such a good list of publications,
Thank you, sir.
which is really rare nowadays. Because again, I will come back to the topic. Okay, topic is not that journal which you have selected, and that is the beauty of this work. And you have done that very good. Uh, one more question. Can I ask one question on this occasion, Chairman, sir?
Yeah. Can ask question, sir.
Yeah, thank you.
Yeah.
Suhail, Saab,
Yes, sir.
you have used this HDF as a measure for major measure for this evaluating the performance of modulation techniques,
Yes, sir. Yes, sir.
right? Do you
Yes.
have you find something during this process? Any such other indices may be proposed which may support this very specific type of work which you have performed, because
So
HDF
the
is a common parameter. I'm not saying why you have done use that. It is a standard practice. That's why this is used. But sometimes
Mhm.
what happens during the research process, researcher comes to know that this particular additional indices is also very supportive, though it may not be general, but for my work. So,
Yes, sir.
जी बताइए.
Another indices that can be evaluating any PWM technique, that is first of all common mode voltage technique. Common mode, you can evaluate the PWM technique based on common mode. The another thing is that you can also evaluate the PWM technique based on torque ripple. Which PWM technique produce the highest torque ripple that can be avoided, and that PWM technique that can reduce the torque ripple that can be selected. The third or maybe possible widely utilized parameter, that is switching loss. The PWM technique that can reduce the switching loss effectively, that can be selected. And the fourth parameter, that is HDF, or you can say that stator current distortion. Based on that also you can select the PWM technique. So these are the some parameter, based on that we can select the PWM.
Good. I appreciate. And no questions from more questions from my side, Chairman, sir. I do agree with the compliance report submitted by the supervisor, sir. Thank you very much.
Thank you very much. Thank you. Now I will request Madam Chudamani here. She is internal examiner for the PhD student. I would request Madam to kindly have your question answer first, and then I will ask her to have some question answer session for the questions given by the external examiner from abroad. So, Madam, kindly.
Sheikh Suhail, have you prepared any response sheet for the questions to be asked at the time of Viva OC? Because you would have been communicated by,
Yes, ma'am.
yeah. Have you prepared any response sheet for this?
Yes, sir. I have. Yes, ma'am. I have prepared response sheet.
Yeah, can you please show, do you have response sheet? If you can present it, can you present it?
Yes, ma'am.
Yeah.
Here it is, ma'am.
So why THDs are evaluated for stator current? So can you just scroll down and give a brief answer for each question?
That we are evaluated for stator current because rotor current is not accessible. And the second thing is that rotor current and stator current both are actually scaled down. So whatever the current harmonics that are measured in stator, that is also available in rotor also. The second question was that what is the connection type of 6 Newton meter load, and also stated whether this connection has any effect on THD. So, madam, yes, we have a stator connection, that is a load torque that is applied, that is 6 Newton meter. We have also checked at different loading condition, and the reason is that when you change the loading condition, your harmonic effect on harmonics are going to be increased. So when loading are reduced, harmonics are going to be increased. The third question was that can you describe in percentage terms? So torque ripple is reduced by 76.5%. The fourth question was that detail regarding the sizing of induction machine. So these are the detail that is available on this page. That is, machine has 1.5 kilowatt, 200 volt, 50 hertz. The fifth question was that has your calculation for SVPWM pulses have taken care of any neutral point voltage clamping? So no, ma'am. In our PWM technique, that is the two-level inverter. Generally, multi-level inverter will having a care of neutral point voltage clamping. The sixth question was that whether you have measured at 4.8 kilohertz frequency only, or whether different frequency. So the answer is that we have measured at 4.8 kilohertz. We have also measured at 9.6 kilohertz, 7.2 kilohertz, 6.4 kilohertz. So these are the all frequencies that we have considered during our analysis purpose. The last question was that the loading condition type, that is whether it is star or delta connected. So the question answer was that this is not a star or delta connected. The loading is actually mechanical type of loading that we have used for ultimately apply a loading condition. So these are the all questions that was asked.
Okay. Thank you. So I will
Welcome,
ask you
ma'am.
few simple questions in general,
Yes. Okay.
not specific to your means few questions on your work.
Okay.
First, because you have done on PWM, so can you tell me what is the frequency of the zero sequence component so far as six-phase induction machine is concerned, induction motor is concerned?
Sir, in three
What
phase or
is
six phase case, zero sequence frequency are multiple of three. So that is 150 hertz.
150 hertz?
150 hertz.
Suppose if the number of phases is odd, what relation does it have with the zero sequence? Suppose if you have taken six phase,
Mm-hmm.
okay. Suppose if I have five phase. If I have five phase, is there any relation between the zero sequence component and the number of phases?
Yes, yes, ma'am. In case
Okay.
of five phase, we are having first of all first component. Then we are having a whenever we are having a frequency that is five times the supply frequency, that will be considered as a zero sequence component in five phase.
So another, what is the why you have chosen six phase? Is there any specific reason? Because you can go for odd number of phases, even number of phases.
Mm-hmm.
Reason for going for six phase? Because people report on five phase, seven phase like that. So
Yes,
I
yes,
just
ma'am.
want to know because I also want to know about it.
Mainly, actually, there are the two to three additional benefit for six phase machine. The first
Hmm.
is that the six phase machine can be designed and developed by a three phase conventional inverter. And the second thing is that six phase machine can be reconfigured as three phase machine. These are the second advantage of six phase machine. And the third advantage was the because of six phase machine, we have a elimination of fifth and seventh harmonic torque. That are the reason that why I'm selecting the six phase machine.
So that
In
means
case
if we
of
go,
five phase machine or seven phase machine, we don't have a symmetrical and asymmetrical configuration. While in case of six phase machine, we have symmetrical and asymmetrical configuration. And asymmetrical configuration have additional advantages. And because of that, instead of going for 9 phases or 12 phases, I have selected the lowest one, that is six phase PWM technique or six phase machine.
the major advantage you mean to say is it is convertible from three phase to six phase and vice versa. Is it
Vice
okay?
versa. Yeah, that is okay.
So can you go to slide number 54?
Okay, ma'am. Yes, ma'am.
Yeah. Can you? Yeah. Slide number 54.
Yes, ma'am. This is slide number 54. Oh, sorry.
Please share.
Yes, sorry. I forgot to share. This is slide number 54.
So you have plotted this modulation index in x-axis, and what is on the y-axis?
That is total HDF, harmonic distortion factor.
Okay, harmonic distortion factor. So in some of the curves, it is reaching a peak value for certain modulation index and coming down. And other
Ye-
curves, they are showing an increasing trend. So can you explain this one? Is it, see, for one particular method, there is a peak value of,
Yes,
means the distortion
yes.
is maximum at one particular modulation index, and other methods are not showing such trends, means monotonically increasing trend. So
Yes,
can you
yes,
just,
ma'am. Huh.
yeah,
These, if we observe very carefully, these are the PWM technique 4, 6, and 5. These all are discontinuous PWM technique. So in discontinuous PWM technique, we are having this trend that they can attain the peak value, and after that they are going to be reduced. While in case of continuous, all the continuous PWM technique is having this advantage that they are actually increasing with the increment of modulation index. And the reason behind that, if we want to observe that, because of the harmonic flux trajectory. So when we are having harmonic flux trajectory of continuous PWM technique, when you increase the modulation index, that harmonic flux trajectories are going to be increased continuously, and because of that these trends are going to be observed. While in discontinuous PWM technique, after this interval, the trajectories or the plot of trajectories are going to be reduced, and because of that, they are going to be in downward direction.
so which one will be advantageous? Which one will be advantageous?
The advantages will be depends on, first of all, which leakage coupling coefficient, means what type of machine is there. If we are having a, let us say, zeta equal to 1, means it means that, let us say, we are having permanent magnet synchronous machine, then the advantages is that you have to use hybrid technique. It means that up to this speed use discontinuous PWM technique, and after that at lower speed use continuous PWM technique.
So our objective is to keep the distortion factor as low as possible.
Yes, the
Therefore,
intention is,
up to certain modulation index, the other methods, one group of methods will work, and after beyond that one, another group of methods will work. Okay.
yes,
So if
yes,
you
ma'am.
combine these two, uh, this thing you can achieve a optimum performance.
Optimum
Okay.
performance. Okay.
Yeah, that's all from my side.
Okay, thank you, ma'am.
Okay, so thanks, Swain, for nice presentation and as well as uh, satisfactory question answer session from the examiners.
Thank you,
So,
sir.
on the basis of this, our successful PhD defense examination in presence of our external examiner, Professor Ashish from SVNIT Allahabad, as well as our internal examiner, this Madam Chudamani. Just before declaring the things, I have some. You have audience are there. You have some queries. Ask questions from students. You have some questions. Okay. So, so online audience are also there. Students, if any students or maybe faculty, if they have any questions, please let me know. I think we do not have any questions as such. So, on the basis of our satisfactory answer to these questions given by our examiners, we board, complete board of this examination will recommend you for award of degree in Doctor of Philosophy to our chairman SVNIT. And on this occasion, we all congratulate you for your nice presentation and defending the thesis.
Thank you, sir. Thank
Congratulations.
you.
So let us have a great clap for him. Very nice job. Great.
Thank you, sir. Thank you.
And also, I would like to thank Professor Ashish as well as our internal examiner, Dr. Madam Sudamani, as well as the external examiner from abroad for Mr. Professor Jachin Singh, Jai Govind Singh, Professor Jai Govind Singh for evaluating the thesis and sparing their invaluable time for this defense of examination as well as for evaluating the thesis. So thank you very much. Thank you very much. And wish you all the
Thank you.
best, Suhail, or take care.
Thank,
Okay, great.
thank you, sir. Thank
Thank
you.
you.
Thank you, Chairman, sir. Thank you. Thank you, madam.